Main is the numbers that you can plug into an equation. Okay, got this part? The numbers that you plug in are the domains. Okay, unfortunately, well, or fortunately, for some functions you can substitute any x value and get a real number out. So you're putting a real number into the function. So here we have some real number. You're putting it into this function. Here's your function box. Function box x. And where you're getting out is another real number. And that's called the closure property of the real. That if you put a real number in, you get a real number out. And not like if you put a dog in, you get a dog out. If you put a chicken in, you get a chicken out. If you put a dog in and get a chicken out, then there's a problem. And that's not okay. That means that the dog clearly is not a domain of your function. Because what you're putting out is not the same type of thing as what you're putting in. Okay, so linear equations, quadratic equations, cubic equations, absolute value equations, exponential equations, all of these types of functions you can plug anything into. Okay, y equals 2x minus 4. I can multiply 2 times anything and it gives me a real number. Okay, that's a linear one. I can square anything. Okay, everything is squareable. Positives and negatives, decimals, fractions, it doesn't matter, you can square it. Okay, you can cube anything. Okay, third degree. So all of these fall under something called a polynomial equation. They can have 2 terms or 5 terms or 9 terms, whatever exponents you have up there, that's okay. Okay, absolute value functions. Also, you can plug in any number you want to into an absolute value function. You can take the absolute value of anything. Okay, exponential functions, 4 to the x power 1/3 to the x power. You can raise any number to a power. That is perfectly okay. If these have no domain restrictions, you can do anything, which is why all of these have all reals as their domain. Okay, you can plug in any number you want to. Okay, other functions have restrictions, and that's what we're trying to find, is where are the restrictions, if any, placed on the x values you can plug in. Because what you get out won't be a real number. Like I said, you plug in dog, you get out chicken, that's not okay. Rational functions. So anytime we have a variable in the denominator, you have a rational function. Okay, like y equals 7/x. This is a rational function. There are restrictions we have to put on this. Okay, that's a rational. Logarithmic. A natural log, sorry, ln of x. That's not L, it should be erase that. Natural log. Or log base 4. Okay, these things have restrictions. We can't take the natural log of every single number. We can't divide 7 by everything. We can't take the square roots of everything. Okay, there are some things that we just can't do this with algebraically. It doesn't work. So there are numbers that we have to keep out that we cannot plug in for x. And those are what we're going to try to find. The restrictions. Which numbers cannot be plugged in here. This is the biggest part of this. What number? So these are basically the only 3 functions that you were going to look at. And there's really only 2 of them because we don't talk about logs until January. But these 2 functions especially, we will find the restrictions of. Okay, so here are the restrictions. For all rational functions, the denominator can never be equal to 0. Okay, you cannot have a 0 in the denominator. Can never be equal to 0. Because then that's where it's undefined. Okay, So we need to restrict or throw out any value that makes the denominator equal to 0. Yay. Okay, that one cannot be in there. Okay, in root functions, okay, we can only take the root of positives. Okay, we can only take the root of positive values. When, of course, we talked about when we solve quadratics, you're going to get an imaginary number out. So if we're putting a real number in and getting an imaginary number out, then that's not okay. That's not the closure property. So for all roots, the roots have to be bigger than or equal to 0. And they have to be positive in order to find the domain of a root. Because we can't take the square root of a negative. We can, but it's not the same thing as what we had. Okay, so these are basically our two restrictions on your domains. Domains of rational functions and domains of root functions. Everything else is pretty straightforward. Okay. Rational denominator can't be 0. Roots, the radical has to be positive. So here are some examples. Find the domain of these functions. Okay. What type of a function is this? It's a linear function because it's just an x to the first power. This is a linear function, so the domain of all linear functions is all real values. You can plug anything into this that you want to. You can times 3 by everything that you can ever think about. Any possible number. So it has all reals as its domain. There are no restrictions, in other words. What type of a function is this second one? A second degree polynomial. It's called a what? How about a quadratic? A second degree is a quadratic. I can square anything you ever think of, so that means it also has no restrictions. In other words, you can plug in any number you want to. So it has all reals as its domain. No restrictions means you have all real domains. Any number you want to plug in is just fine. Okay, this is of course a 9th degree polynomial, but it's still a polynomial. Okay, all polynomials, like the slide said, are all real. There are no restrictions. You can raise whatever you want to the 9th power. Nothing keeping you from doing that. Okay, what type of a function is this next one? An absolute value. Are there any restrictions on absolute value? No, there are not. So once again, all reals. And our last one is what type of a function? An exponential. Are there any restrictions on these ones? No. So anytime there are no restrictions, you have all reals as your domain. You can plug in any number that you want, and you're going to get out the same type of number, a real number. Positives, negatives, decimals, fractions, radicals, whatever. Even pies. Okay, so as long as it's one of these types, a linear, a polynomial, an absolute value, an exponential, you have all real as your domain. There are no restrictions. Okay. You have a worldwide passport. You can go anywhere you want. Okay, but these ones, okay, what type of a function is this first example? Where we have the variable in the denominator. notice it because the x is in the denominator. You just say, well, that's strange. Well, it is strange. You have to restrict it. Okay, so what's true is the denominator, which is x plus 2, okay, that's the denominator, this portion down here. The denominator cannot be equal to 0. Okay? The whole entire denominator, whatever this happens to be, cannot be 0. That's our restriction from over here. Remember, the restriction is the denominator cannot be equal to 0. So if you're trying to find that, you set the denominator to not equal to 0. And then you solve it. And this is a very easy thing to solve. So in other words, x cannot be equal to negative 2. Okay? So this is the restriction. You can plug in any number you want to, so all reals, as long as x is not negative 2. Okay? Any number you want to except for negative 2. If negative 2 is the number that makes the denominator equal to 0. So we have to throw that one out. That one is not allowed. That's the restriction. So any number you want to is except for negative 2. Negative 2 is not allowed. Okay, this next one, are we ready to go on? Okay, this is also a rational function because the variable is in the denominator. It's also in the numerator, but it has one in the denominator. As long as there's one in the denominator, you have to restrict it. So what number are we restricting in this case? So the whole entire denominator, 4x plus 16, cannot be equal to 0. So let's solve this for x. Minus 16 minus 16. 4x equals negative 16. Divide by 4. X cannot be equal to negative 4. Okay, so you can plug in any number you want to except for negative 4. Okay, any number is fine here, even into the top. You can plug 4.5 into the top, that's fine to have a 0 on top. It's the bottom that we're concerned about. Any number except for negative 4. So this is a domain, all reals, as long as you're not talking about negative 4. Okay, and this last one, what type of a function is it? Square root function. Notice the square root here. And what's the restriction on square root functions? From a second ago? That this thing cannot be negative. So in other words, x plus 4 must be positive. Okay, you cannot take the square root of a negative. It is not a real value. It is imaginary. So we have to keep this answer, we have to keep the numbers that you plug in real so that you get out a real. So here, x has to be bigger than or equal to negative 4. So we are restricting this one's domain a lot. You cannot plug in any number less than negative 4. Because that will make this thing under here a negative and will make your answer imaginary. When you plug a real in, you have to get a real out. For some reals you plug in, you get imaginary out. That's not okay. So these are your restrictions. Top one, you can't have negative 2. The second one, you can't have negative 4. The bottom one, they have to be bigger than or equal to negative 4 are your restrictions. Okay? So you should know, every time you see one of these types of functions, you must restrict them. Okay? What type of a function is this? Where's the variable? In the bottom, so this is a rational. As long as it has a variable in the bottom, it's a rational function. Okay, yes, it's a polynomial on top and a polynomial on bottom. It's rational. So our restriction is that x squared minus 9, the denominator, cannot be equal to 0. Every time you see a variable in the bottom, the bottom cannot be equal to 0. Okay, in solving this, x squared cannot be equal to 9. So I'm going to take the square root of both sides. X cannot be equal to 3 or negative 3. Because when you take a square root, you get two different answers, a positive and a negative. So the domain is any number you want to except for 3 and negative 3. It's like you have an allergy. If you're lactose intolerant, you can eat anything you want to as long as it doesn't have lactose in it. In milks and cheeses and whatever else they have that has lactose. Or if you have a peanut allergy, you can eat anything you want to except for stuff with peanuts in it. That's the diet. Okay, there are restrictions on your diet. These have restrictions on your variables. Don't want death due to peanuts. No death due to negative. Okay, this is a square root function, so we have to have this be positive. 3x minus 9 must be bigger than or equal to 0. Must be. Because if you plug a real number in, you cannot get an imaginary number out. So 3x has to be bigger than or equal to positive 9. So x must be bigger than or equal to positive 3. Okay, so any number, as long as it is bigger than positive 3 or equal to. Sometimes you don't even have to write the all reals in there, just write that x has to be bigger than positive 3. I will understand. So if we're going to write it as interval notation, we would write it at 3 and then go to infinity. Okay, so if you want interval notation, this would be interval notation. Okay, this is how we're going to write the stuff here in a minute with the graphs. And this third one, this is once again a rational function. The variables in the denominator, so x cubed cannot be equal to 0, which means x cannot be equal to 0. Okay. So basically, there's only two functions that you need to watch out for. Rational functions and radical functions. Because either way, cube rooting it, fifth rooting it, whatever, fourth rooting, even roots, it has to be positive. Okay, rational functions and radical functions are the two to watch out. This one cannot be equal to 0, this one must be positive, bigger than or equal to 0. Okay, and then we have these cute little ones, like we did in Algebra 1 and Algebra 2. Remember the domain are all of your possible x values, so we're going to map this down here to the x-axis. So all these numbers are okay, 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 stop. So the domain would be from parentheses, negative 1, 2, 3, 4, 5, 6. Negative 6 is the leftmost point. 1, 2, 3, 4 is the rightmost point. Okay, so parentheses for open dots, brackets for closed dots. Okay, remember that from Algebra 2? And likewise, the range is when we map it over here to the y-axis. So open dot, color, 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 closed dot. So the range, notice the range has a single staff rather than a double. The range starts at positive 1 and goes up to parenthesis at the open dot, bracket at the close dot. Okay, so these ones are not too tough. These are the traditional ones. Oh, that's a nice flat graph. Let's see if we can determine what's going on here. Come on, look at that one. This is like the 0. I always wonder, why do they have white on top of the color? Instead of black graph. There. Look at that. Okay, so here we have a closed dot. These are all of your x things. X exists. X, 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 X. To here. And then it's like y. We will include this. Okay, so closed dot with the graph. Up, 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 here. No, one more. There we go. Because this is level with this. The highest to the lowest. Now let's change what color we can see. Domain is from -5 to 1, 2, 3. Bracket, bracket. Range is from -1, 2, 3, 4 to 1, 2, 3, 4, 5. Okay, so traditionally when it's given a graph, the interval notation with brackets and parentheses is acceptable and almost always used, but the inequality notation is used when you have equations. Okay, domain and ranges. I think I actually pulled these from an Algebra 2 worksheet. So here's your domain. So right there. Here's your range. Open or closed on the dots? Closed. Because this one is closed, it usurps the open one. So range is from +1, 2, 2, 3, 4, 5, 6. 6, I said. And the domain is from 2, 2, 3, 4, 5, 6. Okay, this one is kind of strange. Notice here we have a domain in between here. So let's account for that one. -1, 2, 3, 4, 5, 6 to -2. But then we have a jump, so we put in this little thing here, union, united with. These things are united. And then this way. Goes on forever. So we can write that from 0 to infinity, and it goes off the page to infinity. Let's see, range will also be a patchwork or a piecewise range. There are two different pieces to the range. There is the piece that goes from 0 to 2. Okay, this piece right here. And then there's the piece that goes from 4 to infinity. Okay, so if your graph has two different pieces, your domain will have two different pieces, and you write a U there to unite them. Union of this set with that set is all your domain. Okay, I know, kind of strange nomenclature, but whatever. What can you do? So this one, here we have all the way over to here, over to here, over to here. It gets closer and closer. Open. There are two ways we can write this one, either using the interval notation from -infinity to 0, and then pick up again at 0 to +infinity. Okay. That's how we say x not equal to 0. So whichever way you want to do it. This is interval notation. This is inequality notation. Not equal to 0. And the range here, what's the range? The range is y values must be positive. Okay, it does never cross this, so we have an open circle here and then all the y values. Or if you will, from 0 to infinity in interval notation. Okay, this one looks like we have a nice one. This is a cubic. If you've noticed, if you are friends with the cubics, you've noticed them. The cubic's domain is all reals. It can go any number you want to, left to right. The cubic's range is also all reals. Okay, it goes on forever, up and down. Okay, so we're going to do some equations and we're going to do some graphs, and you're going to write their domains and their ranges. Okay. Usually the inequalities are left for equations, and the interval notation for